Picking back up with lesson 16.2, our second day, with our example number 2, we're looking at this line integral, and we were very fortunately given the parametrization of x, y, and z. Sometimes, of course, we actually have to do some work to find that. Here, they've been very kind to give that to us. They've even given us the boundaries for t, and that t, of course, is between 0 and 2 pi. So as we evaluate this integral, turning it into the integrals that we've seen in the past, we look at our y here, and our y, of course, is really just going to be the sine of t. We look at the sine of z. Well, z, of course, is a t, so this will become sine of t. And then our ds, well, ds, remember, as we saw earlier, it was dx dt squared plus dy dt squared plus dz dt squared. And as we just come back here, and with a dt at the end, dx dt, of course, is going to be the negative sine of t squared. Dy dt, well, we'll have the cosine of t squared. And then, of course, dz dt is just our 1, which we have that squared. Don't forget our dt here at the end. Now, of course, sine squared plus cosine squared is a 1. And 1 plus 1 is 2, so we'd have a radical 2. I'm going to pull that radical 2 out in front. And then, of course, we've got sine squared of t dt inside. Now, you could, of course, evaluate this integral via a calculator, but it's also very important for us to review how to evaluate integrals of sine squared, or for that matter, with cosine squared. That's really a calculus BC kind of a topic, one that we've done a lot. Sine squared, you might remember, there is a power reduction formula. This would be 1 minus the cosine of t all over 2. And this power reduction, the benefit, of course, is that we no longer have a trig function squared. So I've got my radical 2 over here. Inside the integral, I'm going to separate and make this a 1/2 minus cosine of 2t all over 2. And now I can go ahead and evaluate this integral just using the fundamental theorem of calculus. The antiderivative of 1/2 with respect to t is a 1/2 t. The antiderivative of the cosine of 2t is going to be the sine of 2t, but we have to reverse that chain rule. If I took a derivative, of course, we'd multiply by a power of 2. I'm going to have to divide by another 2. Another 2 will show up in the denominator, and we're going to have a 4 there. Of course, you can always double check if you're right by very quickly taking a derivative. And I advise you to do that. The derivative of 1/2 t is just 1/2. The derivative of sine of 2t is the cosine of 2t, but a 2 comes out, canceling that 4 to get you a 2. Now, thankfully, the 0 down below is going to nicely work out and cancel this whole expression, but plugging in the 2 pi, we'd have 1/2 times a 2 pi. And here we'd have the sine of 4 pi, but we know that the sine of 4 pi is actually a 0. The 2 and the 1/2 cancel, so we'll just be left with a radical 2 pi. Of course, plugging in your 0, the sine of 0 would have been 0. Just a quick talk about that. Finishing up example 3, as we look at the conclusion here, we've greatly reduced the problem, just for the sake of time, to deal not with multiple segments, but just one. This segment C, it's a vertical segment from 3, 4, 5 to 3, 4, 0. And of course, the key to doing line integrals is to, of course, find the parametrization. And when you're dealing with segments, very nicely, you might remember coming full circle here with really what we did with our first chapter in multivariable calculus, where we said, hey, our x parametrically would be x naught plus at, y is y naught plus bt, and z would be z naught plus ct. And of course, our beginning point, x naught, y naught, z naught, we'll have x is equal to a 3, y is equal to a 4, z is equal to a 5. Now, as you're moving from 3 to 3, you're going to notice that delta x, end minus beginning, is 0. And that really helps out tremendously. X is simply 3 plus 0t. Likewise, look at delta y, ending at 4, starting at 4. Likewise, that's also a 0. So your y has not changed at all. Now, z, of course, has changed. You can say that delta z is really end minus beginning. This is really finding the vector ABC that would represent going from our first point to our second point. That's, negative 5. So we'd say negative 5t. And this parametrization, of course, is going to hold true for when t is between 0 and 1. When we create a segment going between 0 and 1 is generally the easy rule of thumb here. X prime of t, you can see, is 0. Y prime of t, likewise, is 0. Z prime of t, well, that's the one non-zero derivative here. The derivative of negative 5t with respect to t is negative 5. So that's very important as we work this out. Remember, we're trying to evaluate this line integral where we've got y dx plus z dy plus x dz. And of course, we could break this all down step by step. We could say we're integrating between 0 and 1. And our y, we can see, is really just a 4. dx, that's really x prime of t dt. Well, that's going to be a 0 dt. My z here, I could definitely see that it's 5 minus 5t. But look at your dy. dy is y prime of t dt. And y prime we just saw was 0, so that's a 0 dt. X is really just a simple 3. And my dz is z prime of t dt. Well, z prime is negative 5. So it doesn't take long for you to look at this and to notice that you're multiplying by 0. Everything's going to be gone except for that constant of negative 15, and you can actually factor that negative 15 out. And we'll say from negative 15, we're going to go between 0 and 1 of just our dt. Fundamental theorem, antiderivative of a 1 is a t, going between 1 and 0. Well, you can see that's 1 minus 0, which is just a 1. 1 times negative 15 is negative 15. And that, in fact, is going to be our final answer. Just to help you out, we did talk briefly about answers to our even problems from 16.2 day 1. And we had those answers right here. We also have new answers for this new assignment, that's 12 and 14. Just wanted to show that to you also.